All right, pre-algebra, we are going to be getting into section 5.2 here, which is going to be comparing rational and irrational numbers. So let's take a look here. We're going to be able to approximate an irrational number in terms of a rational number, and then we will compare in order irrational and rational numbers. When you compare numbers, you're using greater thans, less thans, things like that. So let's jump into it. Let's take a look at number one. If we use a calculator, right, if we put in the square root of 3, it's going to be 1.7320508 dot 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 dot. Okay, remember this is an irrational number, okay, because it does go on forever. There's no repeating patterns, okay, and many square roots, if the number's not a perfect square, it's going to be an irrational number. Okay, so part A, can we explain where the square root of 3 would be in relation to 1.7 and 1.8? So if we have 1.7 and 1.8, okay, and we want to know where's 1.732. Just remember 1.7 and 1.8, you can put zeros after that. You can put as many zeros as you want. So our estimate of 1.732, okay, or that's the actual beginning of the real value on a calculator, that's going to lie somewhere in between, right? It's between 1.70 and 1.80 would be the 1.73. And the connection between these numbers is that the estimates are rational numbers. Right, the 1.7 and the 1.8, those decimals terminate, they end. Okay, they're rational numbers. But the actual value, the actual square root of 3 is irrational. So we're able to at least get an idea of how large a rational number or an irrational number is by comparing it to actual rational numbers. Okay, so it's a little easier to, I think, imagine. 1.7, 1.8. Okay, 1.732 is just somewhere in the middle there. Okay, another example here, can we find an example of a rational number and an irrational number between 4.8 and 4.9? Okay, so if we need an example of a rational number, they just happen to choose 4.859, right? Since it terminates, it can be written as a fraction. Remember, 4.859, any decimal that terminates like that, you can think about tenths place, hundredths, thousandths. So we can write the 4.859 as a number over 1,000, and that, since it's a fraction, that's the definition of a rational number. Okay, can we come up now with an irrational number that's in between 4.8 and 4.9? Sure, we just need to make sure that we comes up with something that does not terminate and does not repeat. Okay, that makes it irrational. So just 4.85, blah, 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 anything you want, just let that decimal go on forever with no repeating pattern. All right, let's try another one on our own. Let's just take a second. Can we give an example of a rational and an irrational number between 2 and 2.1? Okay, so let's just do this here. So let's say we want a rational number first. So a rational number, I know the decimal needs to end or terminate. Okay, so if we're going to be in between 2 and 2.1, remember 2 is really 2.0, and 2.1, of course, is 2.1. So we could go 2.04, okay, or 2.0 anything. Okay, as long as it terminates, it's going to be rational. Okay, and then for an irrational, we just got to make sure that we have, after the 0.4, there's just, no pattern, just a bunch of never-ending decimals. Okay, so why is it always possible, number 2 here, to find another number, rational or irrational, between any two numbers? Well, there are infinitely many numbers between two given numbers, right? We can always just keep adding to the decimal and make the number like more precise or whatever, and we can make it in between. So any numbers that you give me, I could always give you a number in between them by just adding more decimals at the end. All right. What about ordering some numbers from least to greatest? Let's say we have a list of numbers and we need to order them. Okay, here's an example given. The square root of 71, 9.3, the square root of 84, and then 8.1. Okay, and of course we can use a calculator to give the square root values. So the square root of 71 is about 8.4. Okay, the square root of 84 is around 9.2, okay? And we also showed how to estimate these without a calculator as well, right? We showed put them on a number line and find some perfect squares. But once everything is in decimal form, we can now see that in order, it would be the 8.4 would be the lowest number, then 8.4, then 9.2, then 9.3. So just converting those back, the 8.4 was originally given as the square root of 71, and the 9.2 was our estimate for the square root of 84. So that would put them in order. Let's see if we can do one on our own here. Let's take a look at try these B. Okay, and let's do part A first. So with part A, so we have, let me just rewrite the list. We have the square root of 14, the square root of 16, we have the square root of 14, we have 4.1, and we have 3.6. Okay, so let's see what we can do. So do we know the square root of 16? We do. That's a perfect square, right? The square root of 16 is just 4. Okay, what about the square root of 14? Let's think about, can we kind of estimate it? Square root of 14, so I know perfect squares are 9 and then 16. Those are both perfect squares, right? And the square root of 9 is 3. The square root of 16 is 4. So the square root of 14, okay, 14 is definitely closer to 16. So the square root of 14 should be a little closer to 4 than it is to 3. It's probably about 3.8-ish. Okay, I'm just kind of estimating. So let's just go with about 3.8 approximately. And of course, you could use a calculator if we had to be a little more precise. But now that we have all the numbers in decimal format, now it should be a little easier for us to order them, right, from least to greatest. So the smallest number in our list was the 3.6. Okay, then we had, let's see, the 3.8, which was our estimate of the square root of 14. I want to write it as the square root of 14 because that's the way it was given in the problem. I don't want to write the 3.8. Then the next number was the square root of 16, which was, we knew equaled 4, and then 4.1. Okay, can we do one more? Want to do, let's do part C down there, because that one has a little pi in there. Let's talk about that again, just as a refresher. So part C, our values were pi, the square root of 6, 3.4, and the square root of 14. Okay, and let's see what we know about these values. So pi, again, is this irrational 3.14, goes on forever. Okay, the square root of 6. Let's think about that. The square root of 6. So if we think about perfect squares again, 4 and then 9. Okay, the square root of 4 is 2. The square root of 9, of course, is 3. So 6 would be about here, right? Actually, we should probably move that a little bit, shouldn't we? The square root, ask ourselves, is 6 closer to 4 or is it closer to 9? So the 6 is only 2 units away from 4. So it's actually a little closer there, right? So I'm thinking the square root of 6 is going to be a little bit less than 2.5. It might be around 2.4-ish, right? And again, I'm asking myself, or I'm thinking because the 6 is closer to 4, right? It's closer to the square root of 4, which is 2, than it is to the square root of 9. So I'm going to make 6, about 2.4-ish, just as a guess. Okay, and then 3.4 is 3.4, of course. And the square root of 14 then, square root of 14, let's think about that one. That's going to be in between. We actually did that one up here, didn't we? Why don't we stick with our 3.8 estimate of that? Right, and let's see if we can get these in order here. So for our final answer for part C, it looks like the 2.4 is going to be the smallest, right? This one here. So the square root of 6 would come first. Then I think it would have to be, let's see, our pi, right? Pi. Then the 3.4. And then finally the square root of 14. Okay, so that's how I would order each of those if we had to get those in order. All right, let's do a couple more examples. Number 3, we need to complete the comparisons using greater than, less than. Okay, so greater than or less than. Now, I always remember these. Think of the greater than and less than symbol as like an alligator's mouth. It always wants to be open to the larger number. Okay, so if we wanted to compare the square root of 10 and 2.5, okay, so the square root of 10, one way again, use a calculator, the square root of 10, but if let's say we couldn't use a calculator for some reason, okay, so the square root of 10, I know the square root of 9 is 3, right? The square root of 9 equals 3. So that means the square root of 10 needs to be just a little bigger than 3, maybe 3.1, 3.2, something like that. But either way, it's definitely going to be bigger. Look at our problem. We're comparing it to 2.5. Okay, the square root of 10 is definitely bigger than that because the square root of 10 is even bigger than 3. Okay, what about part B? Compare 7 to the square root of 50. Okay, well, I know for that one, I know the square root of 49 equals 7. Okay, so the square root of 50 is going to have to be a little bit bigger than 7. Okay, so that's kind of a way to think about that one. Part C, the cube root of 8 and the cube root of 9. Okay, since they're both cube roots, they're both equal roots, whichever number under the radical symbol, that's a fancy name for the symbol there, the square root symbol or the cube root is called a radical sign. Since the 9 is bigger than the 8, I know the cube root of 9 will be bigger than the cube root of 8. Same thought process with letter D. They're both square roots, so the square root of 110 is going to be bigger than the square root of 66. Okay, so again, just kind of use, when you're estimating these things, use something that you know the value of. You know, if you need to estimate the square root of 10, use your knowledge about the square root of 9. Okay, if you need to know something about the square root of 50 in part B, use the square root of 49 as kind of just a starting point, right? That's how you can get a close value, and it can really help with your estimations. Okay, so the assignment's going to be here. We're going to do numbers 8 through 13. This looks to be like it is page 66. Okay, so that'll be the practice for tonight. All right.